every project workflow has a bottleneck that controls the throughput of that system. Today, we're going to be hearing about some really interesting research being started by our partners at Texas A&M that examines the criticality of understanding bottleneck rates and the variability around that. So presenting her work is Kayla Betcher, who is a PhD student at A&M. So Kayla, welcome, and I'd ask you to share your screen and
Yes.
then allow me to introduce you. So Kayla is a PhD student at A&M, specializing in construction engineering and management within the Zachary Department of Civil and Environmental Engineering. As a first-year PhD student, she began her research under the guidance of Dr. Ivan Damvanajek, our partner there, and she is focusing on optimizing project scheduling through the integration of various quantitative and qualitative methodologies. Her work aims to develop innovative strategies to ensure efficient and timely project completion, contributing to advancements in the field of construction management. So Kayla, I'm going to turn it over to you, and I'll be back for Q&A here in 20 minutes.
Perfect. Thank you so much, Gary. Hello, everyone. I'm so happy to be here today. Thank you for joining my talk on managing project schedule contingencies based on project production data from the Bottleneck resource. I'm looking forward to diving into this topic a little more today in the 30 minutes we have here together. So a little bit about me. My name is Kayla Betcher. I graduated from Texas A&M University with a bachelor's degree in civil engineering with an emphasis in construction engineering and management and a minor in business. After working a few internships over the summer in the land development sector, I realized the intense need for good project management. A good project manager helps out every other aspect of not only the project, but the business run smoother. I knew at the time I wanted to discover more in the realm of project management, so here I am. I'm a first-year PhD student in the Zachary Department of Civil and Environmental Engineering. Thus far, I have focused my research around contingencies and project production scheduling. Unfortunately, my advisor, Dr. Ivan Damjanovic, was not able to make it here today with us, but I would like to thank him for his help that he's put forth on this presentation. So with that, let's get started. So as I began to think about a project and the reasons for failure, two things really came to the top of the list: over schedule and over budget. And unfortunately, these two factors can be pretty hard to control with all of the moving pieces of a project. Sometimes the project even starts off on the wrong foot, leading to overly optimistic expectations, which creates an unrealistic project schedule. Problems can arise later on in the project with labor and material shortages, which I'm sure many of you are familiar with in this day and age. This can lead to a decrease in the production and delay in the overall project schedule. And at times, the project scope might change from the initial estimate, creating more work that needs to be done or redone in order to reach the end completion. So why should we proactively manage project schedules? Because as we know, time is money. Why would we wait around for our schedule to be affected when there may be a way the issues could be prevented? So after I've given you all of these bad ways that we know that can affect our schedule, so how can we estimate completion time for our schedules? Using a simple production model while applying both Bayesian theorem and Erlang distribution, we're able to proactively make changes to our project schedule based on what is occurring in the project. So what is this Bayes law or Bayesian approach that I'm talking about? So simply, it's the idea of updating a belief or outcome based on a previous evidence. So let's take a simple coin toss example to help get a better grasp on the concept. So say we have a coin and we want to know the probability that the flip of the coin will be on heads. Assuming this is an everyday coin, the prior probability, or what we believe will happen before the event takes place, heads and tails are both equally as likely to occur. We can relate this to our initial project budget, which is usually based on historical data or sometimes even expert judgment. After creating a baseline estimate, the event takes place and data is collected in order to determine the posterior probability or revised likelihood of the event occurring based on the new learned data. So again, as you can see, we start with an equally likely probability of heads or tails occurring. We flip the coin twice and observe two instances of heads. This causes our probability of heads to become closer to 1. that estimate now becomes our prior for the next instance of flipping. From the last set of coin flipping, our prior probability of heads is around 1, like we said. After 10 more trials of repeating the same Bayesian approach, there's 8 instances of collected data that shows the outcome to be heads. This pushed the probability of heads away from 1, or to 0.8. Again, we're going to do this again. So with our last posterior of 0.8 now becoming our prior, the data seem to really converge around 0.8. But after more flipping takes place and more data is learned, we only have 11 instances of heads out of 20 events. So it's really changed from our beginning estimate. This causes our posterior to move towards 0.5. And then again, we'll use that 0.5 posterior and now make that our prior estimate in our next set. So again, taking our posterior and making it our prior, we collect outcomes from 30 more events, updating the prior after every instance. We reach a posterior still around 0.55 with 27 instances of heads, but with less variance. You can see how the graph really seems to hone in around 0.45 and 0.65. And this is due to the confidence building in the probability estimate, since there's an ample amount of learned data for the experiment. So in our case, we can actually use the same technique to use our learned project data from our project as it goes on to determine the remaining project duration. Along with Bayesian analysis, Erlang distribution will also be used to update our duration estimate. So Erlang distribution was developed for determining the amount of calls that might be made at the same time to an operator at a switching station for a telephone company. So it's a commonly used in queuing theory and stochastic processes. This distribution is defined by 2 parameters, k, which is the shape in the Erlang distribution, and mu, which is the scale in the Erlang distribution. But today we will define the k as the number of remaining work packages in our project, and mu as the processing rate of our bottleneck resource, or arrival rate, as you will see it mentioned throughout this presentation. So this is used to solve the amount of time it will take till the nth arrival, n being any number that you see. So like today, we will use n equal to 100. So for instance, if you look at our 100 remaining work packages with a processing rate of 0.5, it makes sense for the distribution to center actually around 200. Although when you start taking arrival rates and they begin to change, it gets a little trickier in order to estimate that value. So now that I've talked a little bit about each of the 2 theories that we'll be using, so how do we apply them and use them together to be beneficial in the real world of project management? So the best way to show is by example, so that's what we're going to do today. Meet our system. Our system has 3 activities with differing processing rates. And since activity C1 is a pool, the system creates 2 queues, Q1 and Q2. One before C2 and one before C3. It is important to note that the processing or arrival rate of activity C3 of 0.5 work packages per day is the bottleneck resource that governs the arrival of the completed work packages to the sink. Let me highlight that. So this is our sink, so this would be our bottleneck activity C3. So for our project to be completely finished, 100 work packages must run through this entire system. So we'll take in 1 and then loop back around 2 until it reaches 100. So this schedule for the system is based on a single bottleneck, and we don't assume that our bottleneck will move. So in this simple production model, we are not trying to optimize our production per se, but trying to see the impact that the varying arrivals have on scheduling contingencies. So a simple model like this could be applied for 2 to 4 week or near-term look-ahead schedules as well. Again, we are not defining arrival rate of the bottleneck activity as the arrival rate of the work package at the end of the cycle. So this system will run through 3 different cases with differing processing rates for each case. So let's step into case 1. So for case 1, we assume a processing rate of our bottleneck activity C3 or arrival rate ranging from 0.1 to 0.9 work packages per day, with each case being equally as likely, as you can see in the graph depicted here, which causes our mean estimate or mean expected lambda to be around 0.5 work packages per day. So this assumption is used to create an initial budget duration of around 199 days, which is similar to what we saw in our previous description of the Erlang distribution. So the arrivals to the sink, or the amount of time it takes the work packages to process through activity C3, is random, but stays around 0.5 work packages per day, as you can see in the data here for case 1. So as the project progresses, the confidence in the arrival rate of 0.5 increases, with the probability being around 0.8 after all work packages are completed, providing a great initial prior estimate. So as you can see, as the data starts to go on and on throughout the cycle, and when you get closer to the 100 work packages, and with the arrival rate hovering around 0.5, it really starts to hone in on that 0.5 estimate. And you can actually see that there's less variance as well in the graph. So shown on the graph on the left is the remaining duration given the percentage of work completed. On this graph is shown the optimistic in the green, the pessimistic in the blue, and then the most likely outcome in the yellow, based on our expected process time of our bottleneck resource C3. So in this case, we had no learning, which allowed the process time to stay pretty steady throughout. It is important to note, though, that there's bouncing at the beginning of the graph, around 10 days, until around 20 work packages, because there's a higher confidence based on the learned data that the process time will take around 0.5 work packages per day. So once it really reaches that confidence, that's when you really see that linear remaining duration that converges to 0 here. So in the graph on the right, the initial prior budget in the most likely scenario is shown in the orange flat line. The bouncing of the graph until day 20 is also shown in this graph, reducing static again around day 20. The consistency in the processing time of our work packages in C3 create for an adequate amount of contingency throughout the project duration, with an actual duration of around 202 days when completed. So for case 2, the crews experience a learning curve after the first 10 arrivals. As they become more efficient, the processing time of activity C3 become much faster. In this scenario, we'll actually look at 2 different prior mean estimates, in alternatives A and alternative B. All arrival times remain the same in both alternates. The only thing that will be changing is the initial prior estimate. So for alternative A, we assume all prior mean arrival rates will be equally as likely again before the start of the project, which makes our mean estimate of 0.5 work packages per day. So this again created a baseline mean budget estimate of around 199 days for the project completion prior to any of the activities actually starting. So at the beginning of the project, the arrivals are much slower than the previously predicting, with an expected cumulative mean around 0.16 work packages per day through the first 8 days. This moves the first expected rate estimate to shift farther to the left around 0.3 work packages per day. But then again, as the project goes on, the team really began to learn and hone in on how to do their activities and became faster. And this drastically sped up the rate, ending with a rate around 0.8 work packages per day, which is much higher than our original estimate of 0.5. So as we look at the remaining duration of the case 2 alternative A, there is a peak around day 5. This is due to the poor initial estimate that was much faster than what we thought was taking place. So there is then a fast decline after the learning begins to take place in the processing time. Unlike what would be expected after just looking at the beginning of the project actually finished under the initial estimated duration of 123 days. With the ability to see how the project is performing at the beginning, more resources are able to be allocated in order to help with finishing on time. So for alternative B, the distribution of arrival rates is actually not uniform. So we'll have rates of 0.05, 0.1, and 0.15 having a higher probability of occurrence than the rest of the data. So before the project kickoff, we assume the mean arrival rate for our bottleneck activity, C3, will be 0.14 work packages per day. So this estimate, again, is used to create the initial budgeted timeline of approximately actually 729 days to complete our same 100 work package project. So again, after the first 10 arrivals, learning occurred. It's interesting to note that the expected arrival rate after the first 20 work packages shows a small probability of the rate actually being 0.15 as well as 0.3 due to the initial estimate of 0.14. So the data actually seemed to follow that trend for a split second, and then it provided a minor source of confidence for the rest of the project. But as you can see, as the rate continued to go on, it became faster and really continued to shift to the right. And it ended with similar confidence as what we saw in case 2 alternative A. So as far as the remaining duration, there is a tip towards the beginning of the graph due to the initial prior confidence in the estimate. So this pushed the graph to go higher again after the first 5 work packages are completed, and then begin to dip again around 10 work packages when the learning occurred, as we saw in case 2 alternative A. So with the mean arrival rate being around 0.8 work packages per day, there is a huge release in contingency that could take place as you see the area under the orange line here. It's almost more than half of the contingency by just day 25 of the project. So when you're comparing both cases together, it's actually interesting that after the first 20 days, both of the graphs really seem to stabilize together. So this shows that the importance of closely monitoring your projects at the beginning of their life cycle, and even if your initial estimate is off, the monitoring could save your project schedule. And lastly, for case 3, the initial estimate is the same as case 1 and case 2 alternative A, all equally as likely with a mean around 0.5 work packages per day. The arrivals in this case begin very fast, but then begin to slow down as time progressed throughout the project. The arrival rate began with converging around 0.9 here on the very right of the graph. But then as time continued to go on, it really converged more to the left again as it became slower. So the initial budget was again around 199 days to complete the whole project. With the fast rate at the beginning, the project seemed like it was doing really good and fine until it started to lose learning around day 20, which actually caused a serious incline, pushing the actual project duration to around 478 days. The initial estimate created false optimism about the project's total duration, which proved detrimental to the project. Without updating contingencies, the project would significantly exceed the budgeted duration. However, since the arrival rates are updated after each completed work package, budget is dynamic, the project manager could be remain aware of the situation. This allows the project manager to allocate additional resources to prevent the project from running over budget. So after all these cases, what can we actually gather from all of these results? Traditional project management practices with static contingency measures must be left in the past. They do not accurately quantify the importance of understanding the bottleneck resource in your system and how it plays the role in determining your project duration. A simple production model like the one we used can be used to estimate project contingency. Whenever you learn new data in a project, it should always be incorporated to update contingency. It is also so important to take your initial project estimate very seriously. I know at times it can sometimes seem so small in comparison to the bigger picture, but correct prior estimates help converge towards your actual true contingency. The model that we use today can be readily applicable for simple project production models with near-term look-ahead schedules. And lastly, always remember that contingency management is dynamic, just as the projects that we face. And with that, that's all I have for today. Thank you for being so attentive and listening. I hope you can take something away from this that can help you in challenges that you face in your everyday work. And then I also included my email on the bottom. If anybody has any questions that they don't get asked today, they can send me an email and I'll be happy to answer those. Thank you so much.
All right, Kayla, thank you. That was very interesting work you've got started there. And we're going to talk a minute about where you're going with the research. What do you see next? We've got a couple of questions for you. One is, your analysis assumes that the work packages are the same size, I think. Random size variations would act just like variation in processing time. Do you have any thoughts on how you would discover some kind of systematic variation in size? This matters because of the mix of different kinds of work packages varies over the course of the project.
Yes, exactly. We've thought about that as we've gone through this research. Unfortunately, we haven't been able to change the size of our work packages that are going through our cycle. I know when you want to try to apply this to a real world work environment, it's going to be very crucial in doing that. Not all work packages are the same, they all change. But unfortunately, we haven't gotten to that point yet, but that is part of our future research that we're getting started on.
All right. So another question, why is the assumption that the work packages come in randomly?
So for our case one case one, we assumed that our work packages would come in randomly, but still kept the mean estimate around 0.5 work packages per day. So we're randomly as saying they're not coming every half a minute or every half a day. They're coming at you could say anything that the mean estimate would be to 0.5. So 0.44, 0.68, 0.6. So anything, they can come in at any time randomly, but their mean estimate will still be around 0.5. Does that answer your question? Does that make sense?
I think so. And basically you made an assumption for your analysis that they would come in randomly. There could be all kinds of factors in the real world that would cause that randomness to occur.
Yes, exactly. For a project, you're not in the real world, you're not going to have a work package that comes every single, whatever your estimated duration is on the dot. So we wanted to try to kind of make that and quantify that in our research by putting the work packages coming in randomly.
Right. So you're attempting to model that.
Yes.
Another question, it seems to be applicable in high volume activities. What's the minimum you would apply for this technique?
So as we were going through all of our work packages, like the reiterations of the Bayesian analysis, it was really interesting to see after, like I said, 20 work packages, you really kind of got an idea of what was really going on in your project model. So as you can see, like when we compared case one or case two, alternative A and alternative B, we started with two different prior mean estimates. One that was the same as the other ones that we had been seeing, and then one that was a lot lower. And using both of those, you could see that after about day 20, they really started to kind of follow the same path. So I would say as long as you had more than 20 work packages, you could see this being beneficial in your project.
Okay. So one thing that that I took away from your work, and of course I've had the privilege of reading the paper, so I've got a little bit of even deeper insight, is just how important almost goes without saying, you understand where the bottleneck is. You have a bottleneck and it exists. Yeah. But then understanding the assumptions around that bottleneck rate is extremely important to the throughput of that production system. So what are your thoughts on what a project can do to beat the 20, to understand more accurately what that bottleneck rate is going to be before the project starts or as it's getting started?
Yes, of course. So most of the time when you're starting a project, or what I've seen in my experience, is you'll either go back to historical data and look at prior projects and how those prior projects played out. We know that not all projects are the same and they all have different variables that will make those factors a little different, but it's at least a good baseline estimate. But sometimes you'll run into projects that you need a baseline estimate number. You're in a hurry to get that prior budget and all of your stuff out for that project. And you might just grab a number that you think is about right, but maybe you haven't done the full analysis into what has actually made that budgeted estimate number or schedule estimate number what it is. So I think it's really important to go in and behind the scenes and actually dig into all of the factors that created that schedule and make sure that's actually something that can apply to your new project that you're starting or you're working on. You don't want to just pull a number that you think might be close, because as you can see, your prior estimate actually has a lot to do with how your entire budgeted schedule will turn on the end. And that really has an effect on your entire project schedule.
Yeah, another technique I'd throw out there is a first run study of something you're gonna do multiple times. Do an experiment.
Yes,
We
yes.
get real data from your actual situation to inform
Yes,
yourself.
exactly.
Yeah.
Yes, as you can see, the first 20 days of the project really shown from my research to be the most crucial. So you don't want to not, just because it's at the beginning stages of the project, you don't want to not do all of the analysis you can and just kind of let it ride. You don't want to be in that let it ride mentality, because it could really prove to be detrimental. And also we've seen a lot of times that say that our project is performing really well at the beginning and you're doing in the let it ride mentality, when you actually could have taken some of that project schedule contingency and applied it somewhere else. Most of the times when you leave that contingency in that project that it was made for, it ends up getting used even though it might have not needed to be. So it's really important to really hone in on your first, especially 20 days or 20th% of work packages completed.
So where do you see the research going? What are your next steps? What are the next kind of things you're going to look at?
Yes, so I'm actually really excited about where our research is going. We haven't gotten to get as far as we wanted to, just with a few hiccups in summer and travels and such. But I'm hoping to account for cycle time and work in process in my model to rework risk and impact on completion times for the overall model system. And then I also want to make the model more complex, make a more complex production system, like you said, that could be maybe more applicable to real life situations. And then we're also right now, we're looking, our processing time is at an exponential distribution. We want to try to use differing distributions to also model those cycle times. And then lastly, again, it's really important we want to try to account for moving bottlenecks throughout the project as well, instead of just having that one static bottleneck, because I feel like it has a project is very dynamic, so we need to make our model very dynamic.
Interesting. Well, we'll probably see another paper next year.
Yes, I hope so.
All right. Well, thank you very much for taking the time to present your work, and very, very interesting stuff. So all the best in your next step in the research.
Thank you so much.